Yeah, so this is based on some joint work that I did with Chris Moore, who was speaking here, when was that, last week? That is, it's 2 papers on the archive, and we're working on sending it somewhere. But I think it's a very cute proof, and so I'm very happy to be able to share it with people. So before we get there, just some background. So, okay, we all know how to multiply matrices, but today we're going to be interested in how efficiently we can multiply matrices. And so the basic thing is, you do a dot product of a row with a column, and you do n squared of those. And each dot product takes n multiplications and n-1 additions. And so in total, this gives us n cubed steps. And the question is, can you do better than this? In the 60s, they actually proved that if you sort of limit your model of computation to things that they thought were natural, like only working on rows and columns as a whole, that actually you can't do better than this. So if sort of all you're doing is some linear combinations of dot products and things like that, of rows and columns, you can't do better. And then in 1969, Strassen showed you could do better. You could get n to the log base 2 of 7, which is something like n to the 2.1. Okay, and here, for most of this talk, I'm just going to be focusing on the number of arithmetic operations, so multiplications and additions. There's a question of, sorry, I forgot. Okay, motivation, yeah, this comes from all over the place. When we write grant applications, we say, oh, this is used in all of these things. That's actually true, and matrix multiplication can even be the bottleneck, but there are a few things. First is, in practice, you often have sparse or structured matrices. And for those, you often have much better algorithms, right? And so this n cubed thing is just not relevant because you can do it in linear time if you have, structured, highly structured matrices. The other thing is, even for dense and unstructured matrices, the number of operations is actually less of a bottleneck in practice than things like memory and communication. Nonetheless, Strassen's algorithm is actually simple enough that you can use it in practice. So when the matrices are big enough, you can actually use it. But essentially, all of the other algorithms that I'm going to mention when I do this little brief history here are not. They have very large hidden constants, and the memory and communication issues kill them. But the point is, Strassen's algorithm is, and so in principle, future ones could also be. But the real thing is, okay, sure, matrix multiplication is used in all these applications, but somehow number of operations is not the right thing to look at. But the real thing is, matrix multiplication is a very basic operation. And by understanding the computational complexity here, we're gaining some insight into some fundamental nature of this very basic operation. Okay, so with that in mind, I want to come back to, now we're just going to focus on number of operations. And for this, we measure this by what's called the exponent of matrix multiplication. So omega, and omega really is like the standard letter people use. It's the smallest exponent such that you can multiply n by n matrices in n to the omega time. And okay, technically I have it's n to the omega plus epsilon for all epsilon greater than 0. There's a theorem of Coppersmith and Winograd that says whatever the value of omega is, it is truly an infimum. And so you can't actually get exactly n to the omega, but you can get n to the omega plus epsilon for any epsilon you want. Okay, and the folklore conjecture is that omega equals 2 here. And on the one hand, this should be somewhat surprising in that it's telling you that you could multiply matrices essentially as fast as you can add them. And multiplying matrices just seems harder than adding matrices, right? So in some sense, this should be surprising. In terms of the history, we'll see maybe this is a little less surprising. The other thing is I haven't said anything so far about what field we're working over, or ring. And in principle, the value of omega depends on the characteristic of the field. We know that if you're over fields, actually, it doesn't depend on more than the characteristic. It can only depend on the characteristic. But we also don't know any examples where something different happens in different characteristics. So for the rest of this talk, I'm just going to focus on the complex numbers. But like I said, for sort of the history of omega, we don't know any examples where, oh, in characteristic 2, something weird happens or things like that. Okay, so what's the history here? So, okay, prior to 1969, we knew that omega was at most 3. This 2.81 here, this was Strassen's algorithm. There was a long series of improvements in the 80s, culminating with results of Coppersmith and Winograd that brought some interesting additive combinatorics into it. And then there was a long period of time where nothing was happening. And then we got these like very slight improvements in the last decade or so, culminating with a new paper just this year by Josh Allman and Virginia Vasilevska-Williams, saying that omega is at most 2.372859. And as you might tell from the slope of this graph here, the reason I have so many digits is because their improvement here over the previous was in these last 2 digits. Yeah, so from this graph, okay, maybe you would guess actually the true value of omega is 2.35 or something, you know, somewhere in here, because it seems to be leveling off. But we sort of have no good reason to think that it shouldn't get all the way down to 2. Okay, so this is the history, but then what I want to focus on is really this first insight of Strassen's. So Strassen's algorithm, really, the main gain came from multiplying 2x2 matrices better than you think you can. And ordinary 2x2 product, 2x2 matrix product needs 8 multiplications and 4 additions. And Strassen found this thing where you could do 7 multiplications. So each of these terms here, notice it's you're multiplying a matrix A by a matrix B. Each multiplication here is a linear combination of entries of A times a linear combination of entries of B. So he found 7 of these, which you could then take linear combinations of to get the output. And if you work through this, what you see is that here, instead of 8 products, you now have 7 products, but you have 18 additions. And so the question is, why is this, you know, such a big deal? It's like, well, is that better or worse? It's fewer products, but more additions. Turns out that products are really the key metric here. And the reason is that this algorithm works even if the entries are from a non-commutative ring. And that's, again, because every product here is some linear combination of things in A times some linear combination of things in B. And so as long as they all come in the right order, this will work even if the entries here are from a non-commutative ring. And the way you get asymptotic improvement from this is you imagine that the entries come from n by n matrices themselves. So I have 2x2 matrices whose entries are n by n matrices. Okay, and a cute little exercise if you've never thought about this, the ring of 2x2 matrices whose entries come from n by n matrices, it's the same as the ring of 2n by 2n matrices. Okay. So this now says if you can improve 2x2 matrix multiplication, you can recursively do this to improve n by n matrix multiplication. So you can now multiply, say, 2n by 2n matrices using only 7 n by n matrix products and 18 n by n matrix additions. So if we let Rn denote the number of products to multiply n by n matrices and an the number of additions to multiply 2 n by n matrices, you get these recursions. And the key thing you see here is that in the recursive terms, the 7 is the thing that multiplies the recursive term. And so this results in n to the log base 2 of 7 when you work out these recursions, right? And so somehow, yeah, this 18, the fact that you had 18 additions, that shows up here in the constants. But the key thing in terms of the asymptotics is the number of products. And so we're going to focus on the number of products. And the question is, how did Strassen find this, right? If you look at these 7 products, it's like, what? I mean, you can write it down and you can give it as exercise to undergrads to say, verify that this is matrix multiplication. And it's sort of routine calculation and you learn very little from doing that. So how did Strassen find this? Well, turns out people actually asked him. And basically he was trying to prove that it couldn't be done. And you can start trying to do that if you're working, say, mod 2. You can start trying to do it by hand. There are only so many possibilities. And that's what he was doing. And then he found a solution that worked mod 2 with only 7 products. And then you can sort of mess around with the signs to get the signs to work out so that it works in characteristic 0. Okay, and in fact, all of the coefficients are plus minus 1, and so in fact it works over, Strassen's algorithm works over any ring, okay, which is a thing we'll come back to in a bit. Okay, so basically he found this by brute force, right? So not only is there very little insight in verifying this algorithm, but it's not really clear where this should come from. Okay, and so this is, you know, is there some sort of mathematical structure that explains where this comes from? Why this 7 multiplication thing for 2x2 matrices should really exist? And our starting point for this actually comes from geometric complexity theory. Okay, you don't need geometric complexity theory to do this, but this was sort of one of the strands that came together in our heads when we came across this, which is that matrix multiplication is characterized by its symmetries in the following very precise sense. So if you think of matrix multiplication as a map, it's a bilinear map. It takes in 2 matrices A and B and it spits out their product. Well, if in between A and B I put a YY inverse, that doesn't change the product, right? If in front of A, if I multiply A by X, but then I multiply the outcome on the left by X inverse, again, that doesn't change the product. And same on the right for Z. And so these are what I'll call symmetries of matrix multiplication, right? I have the general linear group of n by n invertible matrices, and I can put it in 3 different places, in between A and B, on the left of A, or on the right of B. And what it means that it's characterized by the symmetries is that if you have any bilinear map that takes in 2 matrices and spits out a matrix, and also shares these symmetries, it must be a scalar multiple of matrix multiplication, right? I can't do away with scalar multiples, of course, because scalars just commute with everything. So what this says is if I tell you I have a bilinear map and it has these symmetries, it must be matrix multiplication. And so our starting point, and here was so like, let's use some group theory and some symmetries to try and find algorithms for matrix multiplication. And here I'll make a little side comment. If you don't know about representation theory of finite groups, you can ignore this part and like the rest of the proof will be understandable without this. But if you do, hopefully this adds some insight. So the idea was, say V is an n-dimensional irreducible representation of some finite group G. You can think of n by n matrices as V tensor V star. And if you think of it this way, then you get an action of G on n by n matrices, just like up here we had actions of GLN on n by n matrices. And because V is an irreducible representation, you get this same characterization by symmetries, even if instead of GLN here, I just say I can put a YY inverse and an XX inverse and a ZZ inverse where X, Y, and Z come from G instead of GLN. And so now you could imagine, oh, I'm looking for finite groups and I want some algorithm for matrix multiplication that's invariant under a finite group, and that will guarantee for me that in fact it is matrix multiplication. Okay, so this was sort of the motivation and how we came to this. And now I want to give you the proof. Okay, so to write down the proof, it's a little convenient to rewrite matrix multiplication more symmetrically. And the key thing is I'm going to write it as this tensor. So it's a sum over ijk of eij, where this is the standard matrix with a 1 in position ij and 0s elsewhere. So eij tensor ejk tensor eki, and I sum over all ij and k. Why do I say this is matrix multiplication? Well, if I take 3 matrices A, B, and C, and I look at A tensor B tensor C, and I dot it with this tensor, so this term picks out the ij entry of A, the jk entry of B, and the ki entry of C, and multiplies them together. And when I sum over those, what I get is just the trace of ABC. Okay, it still doesn't quite look like matrix multiplication, but the thing to notice is if I want to multiply A and B, say I want their ik entry, if I plug in eki for C, the ik entry of this product is the trace of A times B times eki. Okay. So this is the object we're going to work with. This is how we're going to represent matrix multiplication. And the idea is we want to write this tensor using fewer summands, because the number of summands here essentially corresponds to the number of products that you use in an algorithm for matrix multiplication. So this expression here, if I'm doing 2 by 2 matrices, I'm summing over 3 indices, each of which takes 2 values. So this has 8 products. This corresponds to the usual sort of naive, row times column algorithm that gives us 8 products to do 2 by 2 matrices. Okay. All right. And now I want to talk a little bit about where these symmetries come from. So if I think of n by n matrices, say I have vector spaces u, v, and w that are all n dimensional, I can think of n by n matrices as just u tensor v star, for example. And so where does this thing live? This thing lives in like u tensor v star. That's one copy of n by n matrices. V tensor w star is another copy of n by n matrices. This is like where my matrix B lives. And w tensor u star, this is where the output lives. And now in this big tensor product, if I re-parenthesize, matrix multiplication, it turns out, is really just a tensor product of 3 identity matrices, but they're sort of twisted. So this identity on U comes from collapsing this U with this U star, which is the same as saying, like, that's why I'm summing over the same index I here and here, right? Okay, and similarly, this identity matrix on V, it's collapsing this V and this V star, which is the fact that the J, the same J, appears in the column index of the first one and the row index of the second one. And the identity on W, same with this K here. Okay. All right. So question so far. So far, this is just, I've rephrased matrix multiplication. I've written it in this very clean, symmetric way. And I'm thinking of it, if in the usual way, it looks like this. But if I sort of twist things a little, it looks like sort of 3 shifted identity matrices. Okay. All right. So now, again, if you like groups, we'll do this. But if you don't, just pay attention to this equation. Suppose G is a finite group, and it has an n-dimensional irrep. So it's acting on C to the n irreducibly, and I'm going to think of this C to the n as before as indexing like the rows and columns of my matrices. And say S is some orbit inside this vector space. If I sum over that orbit, what I get is a matrix that is invariant under the action of G. And so by Schur's lemma, that sum has to be some scalar multiple of the identity. Okay, and if V is a unit vector, then like this is the right normalizing factor. Okay, but the normalizing factor is not going to be too important. It just sort of carries through everything. So what this means is, okay, and if you don't know about groups, then just suppose I have a set S which satisfies this equation. Okay. What this means is if I sum over all triples U, V, W, and S, and I look at the outer product of U with itself, tensor the outer product of V with itself, tensor the outer product of W with itself, I get 3 identity matrices. And we said matrix multiplication is just 3 shifted identity matrices. So if I shift them, so I put the U here and here, the V here and here, and the W here and here. So this is like V here is like the columns of A and the rows of B. The W is the columns of B and the rows of C. If I do this, this gives me matrix multiplication. So great, that's nice, right? Instead of summing over EIJ, EJK, EKI, I can sum over a group orbit. Okay, but the issue here, oh right, and I don't really need to be a group orbit. I just need this equation to hold. The issue here is that this has S cubed summands. And we can already see that's an issue because like we want to do 2 by 2 matrices and we want to beat 8. And like S is not going to have size less than 2 and 2 cubed is already 8. So like this is not yet good for us. But things are nice and symmetric, and we've now written things in terms of group orbits, and so like that feels good. And so instead we're going to consider this sum. Okay, and so let me just walk you through it a little bit. What did I do here? There's still a UV, VW, WU, and the things I've subtracted off are UU, VV, and WW. Okay, why would we look at this sum? Well, on the one hand, it looks kind of like matrix multiplication because it does have these terms UV, VW, WU. It's also, if S is a G orbit, it's almost G cubed invariant. There's some issue with like, well, are these, is G too transitive, and there are some signs here and things, but like it's almost G cubed invariant. So it almost really is matrix multiplication. But the really nice thing about these differences is that it means that I only have to sum over triples of distinct U, V, and W. Because if any two of these are equal, then this becomes 0 and it just disappears. And the number of distinct U, V, and W is now less than S cubed. So there's a hope of beating 8 here. And we'll see that this is going to work. All right, so let's continue with the proof. We're continuing this sum. We have our set S. All right, so now I'm going to expand this out, meaning, this is like U outer product V minus U. So I could rewrite this as U outer product V minus U outer product U, and so on. And if I do that, I get 4 kinds of terms. So I get a matched term if I take the U with the U, the V with the V, and the W with the W. I get a bunch of those. So I'll sum over U, V, and W and get this. I could have one mismatch where like here I'm still doing V and V and W, W, but here I do U and V, right? Or I could do U and V and W, but one mismatch. I could have 2 mismatches. So I could do U with V, V with W, but then W with W. Or I could have 3 mismatches, UV, VW, WU. Okay, and that's it, right? That's all the terms. So let's work out what these are. Okay, if I look at the matched terms and I sum over UV and W, I get, identity, tensor, identity, tensor, identity with a sign, but that's not going to matter much. Okay. If I look at the mismatched terms, UV, VW, WU, and I sum over UV and W, that gives me matrix multiplication, right? This was what we did before. So we would like these other terms to go away because we like almost have matrix multiplication. And the question is, how do we get them to go away? Well, one thing to notice is if I'm summing over UV and W here, in this term, U only appears once, which means I can factor out the sum over U. And the same is true when I have 2 mismatches. So what this tells me is if that sum over U is 0, then the sum over all U, V, and W of things like this is 0, because that sum over U factors out. So this is just what I just said. If the sum over all the vectors in my set is 0, then those 2 middle terms vanish, which is what we want. Okay, and now if this was an orbit of a representation, summing over things in the orbit is just projecting a vector onto the trivial rep. And if this was a non-trivial irrep, that projection has to be 0 because there is no trivial rep to project onto. Okay. All right. Again, if you don't like the representation theory, you can just say this is another condition we want. All right. So what we've just said is if S is an orbit of a group in a non-trivial irrep, then I can write matrix multiplication as this big sum, right? And then I had to cancel off this identity cubed. So in this sum, there was a minus identity cubed, so I have to add that in to get rid of it. Okay. Or if you like, ignore the group part. I just need these 2 conditions on S. So if S satisfies these 2 properties, I get this same thing. I can write matrix multiplication as a sum like this. And these 2 properties are a well-studied thing. A set with these 2 properties is what's called a unitary 2 design. And the reason for that is what these 2 properties are equivalent to is saying I have a finite set of vectors with the property that if I take polynomials up to degree 2 and I integrate any of those polynomials over my set of vectors, it's the same as if I integrated that polynomial over the appropriate unitary group. So this is like a finite set which up to integrating by degree 2 polynomials looks like the unitary group. So if you have a unitary 2 design, you can write matrix multiplication like this. And how many terms does this have? Well, so this is our main theorem. If I have a unitary 2 design of size S inside C to the n, then n by n matrices can be multiplied in S times S minus 1 times S minus 2 plus 1 multiplications, because this is that identity cube term that we had to add in. Okay, and what we said, if you were following the thread about finite groups, is if G is a finite group and V is a non-trivial irrep, then any orbit in there is a unitary 2 design. Right? So you can find unitary 2 designs sort of in abundance. And what's the smallest one we can think of? Well, the action of S3 on a two-dimensional vector space has an orbit of size 3, namely the corners of an equilateral triangle. So the corners of an equilateral triangle inside C2 are a unitary 2 design. And if I plug 3 into here, I get 7. Right? And so Strassen's algorithm somehow comes from this unitary 2 design, or if you like, this group orbit. Right? And now there's like some real structure to this. Okay, I didn't write down the exact equations for you, but the point is there's a nice mathematical object sitting here that gives you this 7 multiplications. You can also generalize this, like the symmetric group always has an orbit of size n plus 1 in C to the n, which are like the corners of a equilateral simplex. And so that gives you n cubed minus n plus 1, which beats the trivial n cubed, but not by much. And like we know algorithms that are much better than this. But the interesting thing here is like not only do we have structure, but this structure generalizes. Okay, now you might ask, is that really the same as Strassen's algorithm, right? I just showed you this thing where we said we take an orbit of a group and you look at this equation and you see that it gives you what you want. And then at the beginning, I showed you here are the 7 multiplications from Strassen's algorithm. It turns out that the answer is yes. So there's a theorem of de Groot from 78 that says any 2 ways of multiplying 2 by 2 matrices with 7 equations, 7 products, are equivalent up to a change of basis. So by this sort of very powerful theorem, yes, it's the same up to change of basis because it also has 7 multiplications and it had to be. But the real thing is kind of, we don't actually care, right? The thing we really cared about was that we're giving some nice mathematical object, some conceptual explanation of where 7 comes from for 2 by 2. Okay, so just to wrap up here, we have this nice mathematical object that gives 7, right? It generalizes to all n. We know how to beat it for bigger n, but like it does generalize. But there are still some questions you can ask. So one thing to notice is the corners of an equilateral triangle need coordinates like a half, a third, and √3. Whereas Strassen only needed plus or minus 1. And so Strassen's algorithm works over arbitrary rings. Ours only works over rings where you can divide by 2 and divide by 3. So one question is there sort of a similarly nice explanation that has some nice mathematical object and generalizes that works over arbitrary rings, right? How could you tell, for example, from our explanation that there's some change of basis that makes all the coordinates plus or minus 1, right? That's not obvious to me. And then the other thing more generally is just, okay, so our thing generalizes, you can do it for bigger n, but it's not optimal. Could you somehow use unitary D designs for D bigger than 2 to get matrix multiplication algorithms for bigger n, right? That do better than n cubed minus n plus 1. Can you somehow take advantage of the additional structure you get for D designs? And these are, again, finite sets where they look like the unitary group up to integration by polynomials of degree D now, instead of just degree 2. And then the other thing, backing up more generally to our original motivation, is just can you somehow leverage symmetry to find new algorithms? And so we are not the only people who worked on this. There are also some very nice papers by Burachenko, and I think now 2 or maybe 3 papers by Ciantini, Eichenmeier, Landsberg, and Ottaviani that are also sort of pursuing this approach of leveraging the symmetries in order to actually find new algorithms. Okay, and yeah, so I think that was everything I wanted to tell you, and I'm happy to talk to anyone about this offline and to take questions.